Okay, so now we're going to look at an example using the definition of a derivative. So remember what a derivative is. It's the slope of the graph of a function. And so to get the slope of the function, we do a very small rise over a very small run, and that is defined as the derivative. Okay? And this is the notation for derivative. And remember that is very similar to a small rise in the function over a small run in the function as this gets to 0. Okay, so what does that mean? So why don't we try a function f of x equals x squared. So we can see the slope of this function at every point in space. Okay, so right now we know kind of what this looks like. And we'll see if this matches our result. Okay, so it just looks like a parabola. I mean, it is a parabola. So this is what we have to look at. So how do we use the limit definition of a derivative to kind of figure out the derivative of this thing? So what we do is just plug it into this formula. So we take limit as h approaches 0 of, put everything in, so x plus h squared minus x squared all over h. Okay. And so we can mess around with this thing, and we get limit as h approaches 0 of x squared plus 2hx plus h squared minus x squared all over h. And so as we continue down, we get more and more precise. And so these cancel. And now we can divide out. Oh, and we know how to do this one. We're just going to substitute in. And so we get that the slope is 2x at every point in this graph. And so what does that really mean? It means that every point on this graph, based on our x position, we can get a slope. Okay, so why don't we estimate the slope right here and pretend it intersects right there. I'm just bad at drawing. So at 0, 2 times 0 equals 0. Oh, look. If we draw a tangent line there, it's 0. And we can try another one. At 1, it should be 1. Sorry, 2. So if this is, let me draw it a little bit more accurate. So if this is 1, this is roughly a slope of 2. I mean, the drawing is not that great. But we can see that the slope keeps increasing as we go this way and keeps getting more negative as we go this way. And that's what we expected. And so we can see that the limit definition of the derivative works very well for simple problems like this.